Hi everybody, this is Ms. Ellsworth. And what we're going to be talking about today is gases. We're going to be extending on to that, but I just want to do a quick little review since it's Monday and we spoke about these last week. Do you remember we talked about how gases diffuse in the air and that you can smell good and bad smells? Well, basically, if you can smell it, that means that there's a chemical because it's diffusing through the air and that's what you're smelling. Sometimes I will go into town, actually to school at night, and there is an awful smell in the air because somebody's burning plastics. And it smells so unhealthy that I try my hardest not to breathe because it's like your body doesn't even want to breathe it. It's because there's chemicals in there. They're not healthy in that situation. And so you know it, and what you're doing is you're breathing in those gas molecules from those different sources, and so it's a chemical. Okay, remember that gases, that they have a mass, but they are compressible is what we're going to be talking about mostly today, and that they fill up their container completely, and that they also are able to pressurize, and the temperature affects them too. Okay, remember we also talked about the kinetic molecular model, that these molecules are moving very fast. It depends actually on the temperature. So the more rapidly that they move is because it's hotter. And so we'll be talking about that specifically, but that all these collisions that they're happening here, it actually keeps the container up. If not, the container would just deflate like a balloon would. And so when a balloon deflates, it's actually because gas particles are leaving the balloon. So they're small particles that have mass, they separate, and they're far apart from each other, and that they're constantly going in this Brownian motion that we talked about before, that they're zinging around in straight lines. That is what the theory is of how that these particles all move, and of course theories are continually supported with data, and we're going to move on to the next thing. Okay, remember I asked you to take a bottle and to put a melted straw in it, okay? And then the straw, I asked you to weight it down and to put it inside of here. Then I asked you also to squeeze the bottle when the cap was off, and you may have gotten a little bit of a mess. I hope you did it over the sink like I asked you to. And then when you put the cap on, then this actually went down, okay? So when this actually went down, that proved that this whole thing is a system. If it wasn't about that, then when you had the cap off, then it wouldn't mean that this whole thing was a system. So that's going to help you in answering this question. And it's also going to help you some more when we talk about two gas laws. And specifically, Boyles Law is the one that will help you describe this one. And Charles Law, well, not so much. Well, anyway, so when you go and you look at this syringe right here, if you would go and put some, well, first of all, seal it off. So it's got some gas molecules in there, and then to seal that off. Okay, then what do? You push on the plunger, and it only goes so far. So hold on here a sec. So it only goes so far. Okay, and then after that, it won't close anymore. I mean, really strong people try it too, but there's gas particles in there, the same amount that there was when this thing was open, and it took up so much volume. So when you increase the pressure, what happens to this volume in here? It gets smaller. And that's really what Boyle's law is about. So as you increase the pressure, what happens? What happens is that the volume decreases. This is an inverse relationship. So vice versa would happen. If I would go and remove this, okay, if I go and remove this, and we're going to talk about now instead, we're going to pull this plunger out. Okay, we're going to pull it out so far. In fact, those same gas particles are in there. And remember, they only want to take a certain size of volume at that temperature. The temperature hasn't changed. So what happens is that you pull on it, and it just doesn't want to go too far. So we're lessening the pressure inside of there. And then what happens as we get that plunger way down here, now our volume has become quite large. Okay, so again, that is an inverse relationship. I'm going to try and fit that in there. is an inverse relationship, meaning as one goes up, the other one goes down. There's an equation for that. In fact, if you would think about the volume in the first situation and the pressure in that first situation, it's got a certain constant. It's got a certain constant for how much gas particles it is there, but the constant is really about what type of gas it is too. So then you go and you increase the pressure on it. Okay, so our volume gets smaller and our pressure gets greater, and this creates another constant too, and they're actually each equal to each other. And it's about the temperature and the type of gas that's inside of there. In fact, I don't even know if the type of gas really even matters as much. Anyway, so how can you graph that? So when I graph it, I'm going to go and push, what's my independent variable? Well, it's pushing on here. So it's going to be pressure. And then what's going to happen is my volume is going to change. So that's my dependent variable. So I've got a large volume in there right now. Okay, and low pressure. And then I go and I push this up there, and then my pressure is increasing. And my volume is decreasing. My pressure is increasing, volume is decreasing. Okay, and then I'm going to push on it some more, and my pressure is increasing some more, and it's making that volume inside the tip of it smaller. And then it keeps on happening. Okay, it'll never reach zero because you can't ever push this all the way to zero because there are gas particles in there that are pushing against it. They create a pressure. Anyway, so if you would go and graph this, that's ugly, but you get the point. It's got a curve going on there. And if you go and graph it, then that means that we are showing an inverse relationship, or else an inverse proportion or an inverse variation, depending on whether you're in math or science. So it's an inverse variation, it varies inversely, or proportion. I use both terms because, of course, I'm a math teacher also, so I use both terms. One of these days, I would just love it if math and science have the same exact meanings, or same exact terms for the same meanings. Okay, anyway, so that right there is Boyles Law. And if you think about that, you've got some pressure going on inside that straw of your bottle. So that's why Boyles Law is related to that system that's going on. You've got volume and you've got pressure going on in there. Now, Charles' Law has got a couple of different things going on too, but it's not pressure and volume. It's actually temperature and volume. So you guys did that Phet Lab simulation where you went and increased the temperature, and what happens? Oh, this goes up, doesn't it? So it increases in volume. So as you increase the temperature, okay, what happened? You increase the volume. Now, this is thermal expansion. The thermal expansion we've talked about a long time ago in physical science. We've talked about thermal expansion, that when you heat up a solid or a liquid, that it actually increases its volume. In fact, you'll hear about in the cities when the temperature gets really hot that the roads, the asphalt gets so, you can expand so greatly that it starts to buckle and it creates quite a hazard. And so they have to go and remove it and fill it up again. And so all things solid expand as you add heat to it. All things liquid expand as you add heat to it, except for water. Water is different because as you decrease the heat, it should be condensing and getting smaller and smaller and smaller, and then all of a sudden at one point it becomes ice, and ice floats. So it got larger in that case. So, but most things, I suppose if I say all, that we'll find something else that doesn't work. Most things, as you heat it up, it expands, and as you cool it down, it contracts. And everything has got their own thermal expansion rate. But gases, they all behave the same. It just depends on which gas you're talking about. So let's go ahead and look at this one's formula. Okay, so we've got volume over temperature, and this is the first situation. Oops, I better put a 1 there. Okay, now let's talk about this balloon. Okay, so let's say it's January. You go and you buy this balloon at a local store, and so when you buy it in the store, it looks all puffy and big and like it's got plenty of gas in there, and it's got some pressure on the outside of it. And so then you go take it outside, and what happens, it actually looks like it deflates. Well, all of these gas particles are are colder, so they're contracting. So now it looks like your balloon has deflated, kind of deflates your attitude towards about it too. And then as soon as you bring it back inside into another building or the same building, then it actually expands and gets nice, and the balloon is tight, stretched tight again. And so that second situation is what we're talking about. Now that is for that gas. It's got its own constant. So this gas, when it's inflated and then you take it outside and then it contracts, it has the same exact constant. Okay, we can graph this one too. And it's not quite what you expect, but the temperature, as you change the temperature, it's going to change the volume. This is our independent variable. The volume is our dependent variable. So what we know about a direct proportion, because it's a direct variation, it's a direct proportion, direct relationship, is that it comes from 0 and that it goes to whatever point that it is, depending on the type of gas. Now that's not quite what you expect, because this goes down much further than what you think. If we were going to be talking about this would be in Kelvin, which is a temperature scale for chemistry and other sciences. But then we talk about Celsius, where freezing is 0. Okay, and that'd be at 0. And so at Celsius, it's like 273 degrees from here. So Kelvin is really the temperature that's listed on our periodic table. It is the SI unit for temperature, but we always talk about Celsius. They're the same exact sized degrees, but they are measured from 0 right here. Now let me talk about absolute 0 again. Okay, so this is for like helium, that being a balloon, and I have no idea where all of these are supposed to be, but a different gas would have another value, and another gas would have another value. They'd have their own expansion rate so that you could actually identify them. But this absolute 0 that we're talking about right here, you can never reach absolute 0. If you could actually reach absolute 0, then you would actually, molecules would cease to vibrate. They'd cease to move, and so then they'd cease to exist, theoretically. Well, up until a couple years ago, they said that you could never get there, and they got within a millionth of a degree of it, but they never got it. And then a couple years ago, a group actually was able to do something with magnetism on that, and they actually got to go below absolute 0. So they were saying, hey people, we want you to investigate this, and I have never checked into it any further. And so I don't know how that would happen. I was learning physics, and so it was kind of physicists and chemists were kind of getting all upset about this, because that really changes a lot of the rules and laws in physics and chemistry. And so I don't know whatever happened about that, but I should go and look into that someday. Maybe you want to check it out too. Did they actually achieve below absolute 0? Because theoretically that shouldn't be able to happen. Anyway, I'm going to go ahead and move on to this and talk about our bottle again. Excuse me. So here's our bottle, and so we put that straw in there. We know that there's a system because when we had the gas, when we went and pressed it with the lid off, it did not, it spilled, it made a mess. It didn't do anything to the straw. And then when you go and you cap it again, you put your pressure on here, okay, and then your straw would go down. Okay, if it doesn't quite go down and you've still got it all set up, shake it up a little bit. Get a little bit more water in here so that it's got more weight in it. That makes sense, because here you've got gas in here and here's water in here. And so that water actually is more dense than the gas. So then if you get a little bit higher water content in there, my video is going to run out of time, so I'm going to be a little bit quick here. So if you press on the sides, it actually pushes the water level up in there and compresses this gas a little bit more. So use that information and the information you know about Boyles Law to explain why that goes down. And that'd be the third question with that set of series that I gave you last Friday. Okay, and that's all I can get for you today. I'll make tomorrow's lesson a little bit shorter since I went a little bit long today. Bye now. Over and out. This is Mrs. Ellsworth.